Welcome to the video on limits at infinity and curve sketching. The objectives for this video are to determine limits at infinity and then analyze and sketch a function. Most of this video is going to talk about the limits and then the analysis, and we'll talk about how to do the sketching aspect of it and do a couple of examples of the analysis in class next time. Let's first talk about what it means to be a limit at infinity. We're going to let L be a real number. And then if we say the limit as x approaches infinity of f of x equals L, means that for each epsilon greater than 0, there is an m greater than 0, such that if the absolute value of f of x minus L is less than epsilon, that's going to happen whenever x is greater than m. So in other words, that I know if I put in x values bigger than m, I am going to get function values within epsilon units of L. Then we look at the other one going in the other direction, the limit as x approaches, that is negative infinity. This is supposed to be a negative infinity of f of x equals L, means that for each epsilon greater than 0, there is an n less than 0. Notice the less than, such that if the absolute value of f of x minus L is less than epsilon, that's going to happen whenever x is less than n. So in other words, I'm going to have some negative number. And if I put in values that are smaller than that negative number, I will be within epsilon units of L. Let's take a moment and look at what those definitions mean. And without losing any generality, we will just look at the idea that the limit as f of x approaches x from the limit as x approaches infinity from of f of x equals L. So when we look at that, what's happening here is that as we put in larger values of x, my function is approaching this line y equals L. It's really a horizontal asymptote. And what's happening on this, it's continuing on like that. If I go epsilon units above or below L, I will be at epsilon units above, I'll be here. Well, that's not really going to come into play because we don't have any graph of a function, no portion of the graph of that function is up there. But if I look at L minus epsilon, I'm right here, and I can go across and hit the curve and come down. And I know now that if I'll call that m, if I put in any value for x, that's bigger than m, so anything over here, I'm going to get a function value that falls between L and L minus epsilon. And so that's what it means so as I keep moving here, I go through, I can make epsilon smaller, I could come across, come down, and I would get even a bigger m. But as long as I put in numbers bigger than that, I will always be within epsilon units of L. Now we already kind of alluded to this, that line, that limit actually does have a name. If the limit as x approaches negative infinity of f of x equals L, or the limit as x approaches positive infinity of f of x equals L, then we say y equals L is a horizontal asymptote of f of x. So if that limit does exist, then I know that's going to be my horizontal asymptote. Now that we know what a horizontal asymptote is, we now need to find them. And so the first thing we do is we're going to look at the degree of the numerator and denominator of that rational function. So if the degree of the numerator is less than the degree of the denominator, then the limit of that rational function is y equals 0. And if that's the case, then the horizontal asymptote is going to be y equals 0 as well. If the degree of the numerator is equal to the degree of the denominator, then the limit of the rational function is going to be the ratio of the leading coefficients. So let's say the leading coefficient in the numerator was p, the leading coefficient of the denominator was q, then I would say my horizontal asymptote is going to be y equals whatever p is over q. And the last one, if the degree of the numerator is greater than the degree of the denominator, then the limit of the rational function does not exist, and therefore there will not be any horizontal asymptote. Let's take a look at a couple of examples. In the first one here, we're looking at f of x, and f of x is equal to 2x over x squared minus 3. In this situation here, we're going to take the limit then as x goes to infinity of 2x over x squared minus 3. Well, since in this case the numerator has a degree of 1 and the denominator is 2, I know it has a degree of 2, then I know that this limit here exists, but that limit is 0. And so therefore my horizontal asymptote is just going to be y equals 0. In the second one, g of x equals 3x squared minus 7x plus 2 over 5x squared minus x plus 9. Well, then if I take the limit on that as x goes towards infinity of 3x squared minus 7x plus 2 over 5x squared minus x plus 9. In this case, the degree of the numerator and denominator are the same, and so I know my limit is just going to be the ratio of their leading coefficients. So in this case, that limit is going to come out to be 3 over 5. And so my horizontal asymptote is going to be y equals 3/5. In the third example, the degree of my numerator is 3, the denominator is 2. Since the numerator has a higher degree, the limit here, the limit as x approaches infinity of h of x does not exist. And so therefore, there is no horizontal asymptote. Now let's take a look and just talk real quick about the analysis of a function. What you're going to do is you're going to analyze this function, identify its behavior, important locations, where it has max mins, points of inflection, so forth. And then we're going to use that information to sketch the function. So the thing that we have to remember here is that in terms of material, there's nothing new here. We are just using the information that we have been working with for the last well, basically since the start of the school year. So what we're going to do to analyze this function, the first thing you have to do is determine the domain and range of the function. Identify values for x that you can use and what you can't use. And get an idea, think about what are the y values, what's going to come out of this thing, what y values get used. The second thing you want to do is determine any intercepts. That would be x-intercepts and y-intercepts. The asymptotes, which we've talked about in terms of either vertical asymptotes, horizontal asymptotes, things like that. And then any symmetry that the graph might have. Is the graph something that's going to be symmetric over the y-axis, or is it symmetric about the origin? So looking at those. And quite honestly, it may not be either of those. It might not have any symmetry at all, but just kind of be aware of that and check for that. The third thing we have to do is determine any relative extrema and function behavior. In other words, we got to identify where this thing will have relative max and mins, identify if that first derivative is 0 or undefined at where it has those relative max or mins, and identify where that function intervals when that function is increasing or decreasing. And that's all by looking. For number 3, we're using the first derivative. We identify where that first derivative is 0 undefined, and then identify when that first derivative is positive and negative. And the last thing we have to do in terms of our analysis is we have to look at the concavity and points of inflection. That's all the second derivative. That's what we were doing last time. So you're going to take that second derivative, you're going to identify where that second derivative is 0 and undefined, and then test for concavity, determine if we have any points of inflections, and if we do, where are they? Determine if the function is concave up, when the function is concave up, and when it's concave down. We're going to look at all that information, and then once we have that information, we can take that information and come up with a reasonable sketch of this function. So, in class next time, that's what we're going to be working with. We will do a couple of examples in terms of looking at the function, taking the derivatives, doing the analysis, and then sketching it. And then most of the time, though, will be spent with you working on those types of problems. So have a good evening, and we will see you at our next class.